Imagine a breakthrough in quantum computing sparked by the elegant yet complex world of advanced mathematics. This is exactly what Utah State University mathematicians Nathan Geer and Matthew Young, along with their global collaborators and students, are passionately pursuing. Over 14 years ago, Geer and his team developed a novel mathematical framework known as non-semisimple topological quantum field theories, TQFTs, originally crafted purely from a mathematical standpoint, driven by the internal logic and aesthetic appeal of the subject. These theories have since evolved into a vibrant area of research with profound implications for physics. Our work began as a purely theoretical exploration, explains Geer, a professor in USU's Department of Mathematics and Statistics. We followed the natural flow of ideas, guided by the beauty and consistency of the mathematics itself, and gradually brought in new collaborators. What's truly remarkable is how this abstract theory has found direct relevance in quantum physics, bridging mathematical physics and opening exciting new avenues for discovery. What sets non-semisimple TQFTs apart is their surprising power compared to the traditional semisimple versions. These newer theories reveal unique properties that could revolutionize our understanding of quantum particles. The thrilling aspect of this discovery is that these novel properties enable us to predict entirely new types of quantum particles, Geer says. This is a perfect example of how pure mathematics can illuminate the mysteries of the physical world. Our findings might be the key to overcoming some of the toughest challenges preventing quantum computing from becoming widespread. The significance of Geer and his team's research has been recognized in prominent publications such as Physics World and Scientific American. These articles highlight recent findings published in Nature Communications by Aaron Lauda, a longtime collaborator and professor at the University of Southern California. Lauda's team applies Geer's TQFT framework to propose a promising strategy to break through current quantum computing limitations. But what exactly are these barriers? To understand, it helps to recall the early days of personal computing. Many will remember the 1982 sci-fi film Tron, which used groundbreaking computer-generated imagery to visualize binary digits, bits, as quirky animated shapes that chirped yes or no while navigating a digital landscape. This imaginative portrayal helped early users grasp the basics of classical computing, which operates on simple, discrete states, either a 0 or a 1. Quantum computing, however, is a whole different beast. It promises exponentially faster and more precise processing by using quantum bits, or qubits, which can exist in multiple states simultaneously and become entangled with one another. This superposition and entanglement enable quantum computers to tackle problems far beyond the reach of classical machines. Yet the very nature of qubits makes them incredibly delicate and prone to errors. Quantum computing depends on our ability to precisely control quantum systems, says Young, an assistant professor in the same department. For instance, we might need to position a tiny particle exactly and keep it stable. The challenge is that any small disturbance can cause errors, making these quantum bits shift or collapse, which disrupts computations. This is where the non-semisimple TQFTs studied by Geer, Young, and their collaborators could make a difference. In theory, TQFTs offer a more robust framework, Geer explains. They distribute information across a more stable structure, which could protect qubits from environmental noise and reduce errors. While these non-semisimple TQFTs have not yet been physically realized, their unique mathematical properties suggest they could lead to the development of superior qubits. This theoretical foundation provides engineers and physicists with a roadmap to search for these new quantum states. Building on this concept, Lauda and his colleagues recently proposed a concrete method to harness non-semisimple TQFTs to create new quasi-particles they call Neglectons. We name them Neglectons because these quasi-particles are overlooked in traditional semisimple approaches, Geer notes. Both Geer and Young have been honored with National Science Foundation Career Awards for their research and continue to delve deeply into the mathematical physics of non-semisimple TQFTs, exploring their potential to transform quantum computing. If neglectons are proven to exist, it would be a dream come true, Geer reflects. Seeing the abstract mathematics we've developed lead to a tangible, real-world discovery would be incredibly rewarding. But here's where it gets controversial. Could the focus on non-semisimple TQFTs and neglectons divert resources from other promising quantum computing approaches? Are we placing too much faith in a mathematical framework that has yet to be physically demonstrated? What do you think? Are neglectons the future of quantum computing, or just an elegant mathematical curiosity? Share your thoughts and join the conversation below.